Testing, testing. Is this thing on? Is this thing on? My microphone was being a little unreliable earlier. So, shows that it's working now. Nice. Having a good time, having a good time. I haven't decided what I want to do today. Looking on the slides because I want to get that watch list done. Debating maybe breaking it into a part 1 and a part 2. Try and focus on putting all the topics people think they know. Nice. Might be some sort of irony. People are more likely to think they know the second half of the series than the first half of the series, because if you ask most people, do you know about addition? I think they'd probably say yes. But if you said, do you know about counting, or do you know about equality? They would think it was a trick question and actually put some thought into it. Yeah, because I get that a lot when I ask people the question about bases. This is one that I do like in person sometimes to people. Is I ask them to start counting, and when they go from 9 to 10, I have them stop and I ask them, why did you do that? Why is that the place where you added a separate digit? It's maybe not a nice thing to do to people exactly, but that's the entry point to help them realize that there are a lot of things that they think they know that they never actually got the deep understanding of. Especially with teenagers. Right? You get a smarty pants in every group that thinks they know everything. And sometimes before you can get them to pay attention, you have to give them a little bit of shock, showing them that they actually don't know the details of something they thought was simple. Of course, sometimes they actually do know the answer, which, I mean, that's fine too. If you don't want to pay attention and it turns out because you actually already do know the material, then I'm not going to object to that. I know. I always found math class to be super tedious. when I was in grade school. And it was not like I didn't dislike it because I thought it was hard or anything. I disliked it because it was really boring if you had already learned all the material. And I was ahead because I was weird and I thought it was a fun and interesting activity to do with my babysitters as an elementary school student was to ask my babysitters what they were doing in their math classes. So I was asking my babysitters to teach me high school level math when I was in elementary school. But the side effect of that was my school didn't have it didn't have classes divided by ability. It was all divided by age. So right, I was in fourth grade. I was 9. Most of the other students were 10. I was consistently the youngest student in my class. My mom got me started in kindergarten. I like the cutoff date for being old enough to just barely be able to join the kindergarten class was, I think, was probably a little bit after my birthday, when my mom basically went in and asked him to make an exception. She was like, I can't keep this kid in preschool anymore. Apparently, I was asking the preschool teachers questions they weren't ready for, and my mom thought it was time to move me into the kindergarten and get me moving up in the grades. Honestly, in retrospect, I probably could have skipped fourth grade entirely, because by the time I was in fourth grade, I had already covered all that material. Even in the topics that I was not good in, I was already ahead by at least a year. The topics that I was good in, I was basically at the college level by the time I was in sixth grade in math and language studies. So I found middle school and most of high school to be really pointless and unpleasant. On the other hand, in some ways, it's really difficult to separate kids into classes by ability, at least with the current system, which I think is really detrimental in mathematics studies. I know I've ranted about this before. Maybe that's the one that I'll work on today. It's not part of the basic math series. And I want to get the basic math series up and running before I start putting out shorts and rants, right? Because if I accidentally create something in a rant or manage to start fights with some of the clickbait series, I want there to be content on the channel for people to watch before they get there. That that's something that I've heard some of the bigger streamers talk about, is that they did something that pulled in an audience before they were ready for an audience, and that it delayed the visibility into the work in a way that they didn't like. So I'm not sure this is the best way to handle that, but I do want, like, my goal for this entire series is not fame and fortune. I don't need that. The thing that I want people to see is the basic math series, right? That's the goal of the series. But that's why I stream, because eventually somebody's gonna stumble in to ask questions. And that's the goal. It's to get questions answered, but I think most people's questions probably stem from gaps in the basic skills. I want to have some impact. I think it would be a little full of myself at this point to think I'm going to have a big impact. I want to have some impact on raising the basic awareness and the basic math skills. And at the very least, it means that when I'm having a conversation with somebody about math and they get completely lost, I can, I can have resources to point them to. That happens sometimes. Where did I put oh, that's about the bottom. That's what it is. Yeah, I'm looking into hiring somebody with design skills to help turn these ideas into something more than just slideshows. Because I don't know that anybody is really drawn to videos about things that are just slideshow presentations. But we've determined several times, I think, that my artistic skills are unusual. Bare bones? Limited. Limited. That's a good word. My art skills are limited. One thing I have found over the years is that my brain processes vector images much better than it does raster images. If you ask me to draw something, even if I have an actual pencil and paper, which is easier than the tablet, I think, my drawing skills are not super good. On the other hand, if you ask me to do technical drawing, to use drafting skills and software instead of drawing skills and software, I'm quite good at that. And I've noticed that a couple of times, even working on things for this series, that right when I was trying to draw a set of stairs or a cardboard box, I just couldn't get the perspective right. When I switched from drawing to drafting, and I said, okay, let's assume that we're going with an isometric perspective, draw out our 30-degree and 90-degree aspect lines, and then we'll set dimensions, right, relative dimensions. We'll say, stairs are this wide and this tall, and the tread is this deep. Right, that I could do. But if you just said, draw a flight of stairs, I couldn't do it. even for non-technical things, I think I get better results when I'm using vector objects instead, because then I can just drop down approximate shapes for what I want and then adjust them until they're actually what I want instead of a bunch of discombobulated shapes. But I've noticed that when people look for art, generally looking for raster art. And I've noticed that even Google's tools here, when you like Google Drawings, it's a vector program. It's all the dropping geometric shapes and lines and curves and things onto the screen. I don't even know if it has freehand drawing. Right? So all of those predefined shapes and lines and curves are vector objects. Right? They're not. I've been using vector and raster as if everybody understands that, but a raster image is like the first generation bitmaps and includes things like JPEGs and PNGs, and that whole family of image types are raster images. So what they're doing with various levels of compression is taking the input image and scanning every pixel in the image and writing down what color is in that pixel. And for a bitmap, that's literally all it is. Like the bitmap file structure is something you can write by hand if you really want to, because it has a header that says, "Hi, I'm a bitmap file," and then it has the height and width of the image, and then it's just a really long list of numbers, and those numbers represent the colors that go in each pixel. These days they may have added a couple of other things to the headers. So one of the things that the more advanced raster image formats do is they have color depth options. So the shallowest, if we're going to go with the depth analogy, the shallowest color depth is 2. It's every pixel is either black or white, and that means that every single binary digit, right, because computers store things with just ones and zeros, every single 0 or 1 in the image part, every 0 is black and every 1 is white. So you could make a black and white image just by sitting there, and after you're done with the header, you just go 0, 1, 0, 1, 0, 0, 1, 1, right? And it automatically wraps around when you get to the end of each line. So you could make simple pixel art. A typical pixel art for a video game is either 8 by 8 or 16 by 16 or 32 by 32. Right? You could just make a grid of ones and zeros, and every square that had a 0 would be a black square, and every square that had a 1 in it would be white. And you could make a black and white pixel art like that. Then color depth, there's actually kind of 2 options, ways to expand color depth beyond black and white. You can add more colors. Right, so the next step is to add red, green, and blue, because that's what our monitors are made up of. They're made of red, green, and blue. Side note, the red, green, and blue pixels in our monitors are specially chosen and adjusted in relative quantity to trick our eyes into thinking that we're seeing more colors than that. But we are not. RGB really is only red, green, and blue. and our eyes are being tricked. I think, yeah, YouTube channel Technology Connections did a really good video on that. It was quite amusing. He was worried that people would think it was fake. It worked so well that it looks fake. Uh, he went out and bought a bunch of monochromatic lights. So lights that only produce one single color, right? A typical white light is, if it's an incandescent or a phosphorescent light, it may have like a broad rainbow spectrum of colors coming out. LED lights tend to be made up of red, green, and blue LEDs, the same as our monitors. So what he did was he got a light that could independently turn on the different colors. You could probably do that with a computer monitor too. But I think he did it with a studio light, which is less expensive than an expensive computer monitor. And also, I'm pretty sure he already had studio lights because he filmed YouTube videos. But he had one where he could independently adjust the ratios of the different colors and show that under pure colors of light, right? Under something that's pure yellow, right? Yellow objects, our eyes would basically treat them as white because they were reflecting all of the color that was available in the scene. Whereas blue objects, which reflect almost no yellow light, would look black. And then you might expect green or orange colored things to look a little bit green or orange, but no, they look gray because they reflect some yellow light. But yellow light was the only color available, so they look the same color as the yellow objects, just dimmer because they don't reflect as much. Yeah, another fun example of that is in many of the rooms of my house, I've installed motion sensing lights, very dim ones, so that if I get up at night, I don't have to turn the overhead lights on because the overhead lights are very bright, and I tend towards lights that are bright and even a little bit blue, as if it was midday sunlight. But if you turn those on in the middle of the night, it disturbs your sleep. It's hard to go back to sleep. So instead of turning the lights on when I get up and go to the kitchen, for instance, to get a drink, my kitchen and the hallway have these motion activated lights, and they're single spectrum red LEDs. So they're very dim and they only have red light. But then that means that everything that I see looks like it's different shades of gray. Because only red things light up brightly, but everything else reflects some red light. But you can't tell the difference between something that's bright red and something that's bright white, because they both reflect the same amount of light. It's kind of interesting. Now, what might be interesting to do is you can get materials that only reflect very narrow wavelengths. That's not a super common property. Most things reflect a little bit of all colors. And they look colored because they reflect one color more than they reflect the others. Not that they don't reflect any of the other colors. But yeah, you can get objects that only reflect, a very narrow range of colors. I wonder if I could acquire any of those for a demonstration. Because the weird thing about those is that they ought to look black under an LED light that looks white. Because LED lights have narrow bands in their red, green, and blue colors. If I got something that was narrow enough to fit in between those colors, like even if it was orange, for instance, right? It was far enough away from the red LED that it didn't reflect red light, and far enough from the green LED that it didn't reflect green light. It would look black. But then if you put it out in sunlight, or an old style incandescent bulb, those both produce broad spectrum light, right? It's smooth for the most part. It doesn't just give you red, green, and blue. There's actually orange light and yellow light and purple light. And, well, purple's actually a little bit of an interesting case, but that's a different topic. Yeah. If you listen to this and you're like, that sounds really interesting, and you don't want to wait for me to put together a video that I may or may not ever get to, yeah, go watch Technology Connections. It's a YouTube channel. Lots of interesting stuff there. We also did, on a related topic, is brown is dark orange. So if you've always wondered why you can't make a light brown, that's another good video. And the short answer is it's because if you make brown light, you end up with orange. Right? Saturated brown. That's something you can see if you go to a color picker, kind of. I open up a drawings. Put a rectangular on the screen. Let's say, show me some custom colors that I can have. Put the color picker in the middle of the screen to make it hard to see my object, and don't let me move it. No, wait, why did I say that? That's a little frustrating. Right, there's no brown on this sliding scale. We go over here. Right, we'll find most of these colors don't have anything that we would call brown until we get over to about orange. Right. And then if we want brown, brown is full saturation, but turn down the lightness. And then compared to the light colored background, it looks brown. On the other hand, if I shrink that one, change the background as again. Change the background to black. Wait, it's kind of full screen. You make the background black. Doesn't totally show here. Turn the whole screen black. Probably help if I shrunk this down a little bit too, so more black. Right. The darker the area around it looks, the more orange it looks. Then if I change the background to white, now it looks brown. Right. Looks kind of orange. Looks kind of brown. It's kind of orange. It's kind of brown. Trippy, right? Yeah, this is this is one of the effects that works so well that people are worried that it'll come across as fake. Like it almost does look fake. Honestly, this looks brown enough here that I could probably even make it a little bit lighter and more orange colored, and it would stand out. Let's see. How light can I make it? I still have it. See, that looks pretty brown. I'd consider that, a light brown with this background. But then you make the background black. That's definitely orange. Alright, but I'd probably call that brown. Human color perception is very strange. Very, very strange when you get into the details. Yeah, maybe I'll do a video on that sometime. I mostly have math videos lined up, but okay. Videos. Slides. Storyboards.
As I'm in
Yeah,
Say goodbye to your
quiet. Also, stop helping me with that. It's the exact same title. Maybe I'll do it the other way, because I think there's a whole series out there blowing people's minds with how poorly we really perceive the world. It's pretty extreme. His videos are honestly really good, so I'm not sure there's meaning in redoing the things that he's already covered. In some ways, band gaps are a little tough to explain. Because you have to have a basic understanding of how electrons work to really understand band gaps. The short version is electrons have different energy levels. When they're doing their mysterious, swirly, cloud-shaped, not quite a particle existence around the nucleus, they have a fixed amount of energy. Thing is electrons, depending on the atom that they're in and their current energy state, will not accept energy except at very specific values, right? Because when they change their energy level, right, they switch from, how to say it? Okay. Maybe we should start with the idea that electrons don't have a physical size. Okay? Electrons are not, they're not particles in the way that we think of particles. Electrons are kind of fuzzy around the edges. So as an analogy, think about when you're using your GPS on your phone and you lose signal. That's a rough analogy for the quantum nature of very small particles, right? When when they're not connected to the rest of the world, like nobody is looking at them or measuring them, they start to get fuzzy around the edges. Right? So the GPS analogy is, right, your GPS is trying to keep track of where you are, but if it doesn't have a link to the satellites, it's not very precise. Right? So it gets a little bit more and more uncertain as to where it is. So that's why the circle gets bigger. It's telling you, I'm pretty sure you're still inside this circle. Right? But I don't really know where. Now, the difference between an electron and us is that there's kind of a almost philosophical changeover where the electron stops being in a place within its fuzzy cloud orbit and starts to become everywhere in the orbit at a certain probability. Right? This is where people with quantum physics get confused, right? It's the same idea as us with the GPS, right? The GPS, if you have a fancy one, you can set it to, instead of giving you a circle, you can set it to give you a series of shapes nested within each other. And you can tell me where I am with 99.9% probability. Is going to be a fairly large shape, right? So if I put a lot of nines on the end of that, right, my GPS app is pretty sure that I'm on Earth, right? The confidence that it has that I'm somewhere on Earth is 99.9999999 somewhere percent, right? If we chopped all of Earth into small blocks, though, we would find that most of them, the probability that I'm in a given block is very small. Right? So the chance that I'm on the moon, basically zero. The chance that I'm in, say, Los Angeles Town Hall. I assume Los Angeles has a city hall of some sort. Right? I don't know where it is. Never been there. But, right, the odds that I'm there, not too terrible based on what my GPS knows about me. It knows where I live. Side note, I don't live near LA. My nearest big city is New York City, right? So let's take the New York City Hall, right, as the next small patch of ground, right? Based on the last place that my GPS was able to connect, it's much more likely that I'm in New York City Hall than I am in Los Angeles City Hall. Right? So electrons are kind of like that. They kind of have an existence where they're not really, as far as anybody knows, they're not in a given place. There's a list of places where they could be, and each of those locations, has a probability that the electron is there. But for all practical purposes, the electron doesn't actually exist until you try to interact with it. And then it'll interact as if it had been in one of those locations the whole time. But so far as we can tell, it's not actually in those locations. So if there's an 80% chance that the electron is on the left side and a 20% that's on the right side, then if you run the experiment 5 times, aiming at the left side, 4 of those times, on average, you'll get an interaction with the electron. And that 5th time, you won't get an interaction. Right? But then as soon as you stop interacting, right, basically the electron rolls the dice, and it's not in any of those locations anymore. And the next time you try, it'll be a completely new random roll. Every single time you try, it'll randomly select a location And as far as we can tell, it just doesn't exist in between interactions. It diffuses out into not being a particle and it starts being a wave, where it's just like it stops being a thing and starts being a collection of energy that is distributed according to some location like pattern, which is very strange. And that's part of how quantum teleportation works, right? If you put that electron near a solid object, there's a non-zero chance that when it rolls the dice and you try to interact with it, it's going to be on the other side of the solid object. Right? Now keep in mind, solid objects are hard to, like, the more mass an object has in a certain area, right, the more effect it has on the probabilities of all the objects around it. So electrons can do crazy things because they're so small. They can do things that are very unintuitive, right? They have relatively very little effect on the probabilities of things that are not themselves, right? Even so, if you have a very solid object like a sheet of metal, right, there's not a big chance that the electron is going to be on the other side of it, right? Because the sheet of metal does have an impact on the probabilities around it. So going to the other side of the sheet of metal, the probabilities drop off sharply. Right? And the odds that the electron is going to appear inside the sheet of metal is almost zero. Right? Because they're basically, because there's a rule that says electrons are not allowed to overlap, right? So metal sheets have lots of electrons in them, so the chances of our electron appearing inside of some other electron's space is basically zero, because that's not allowed. Why is that not allowed is a little bit complicated, but the short version is because objects with certain properties reject each other. That's the short version, is that there are properties that some objects have, and electrons are one of those objects. Where they reject same type objects, other objects with the same properties, from having, it's called the state, right? Because, as I've been rambling about, location is kind of a fuzzy concept for subatomic particles, right? So at some point it makes more sense to stop thinking about it as position at all. And the name for the distribution of properties that these particles have is their state. Right? And one of the rules is that elementary particles with certain properties cannot share the same state. It's kind of the same as the way that we think about macro scale physical objects can't overlap, right? You can't like walk through a wall. Here's a statement that's not entirely true. The odds that you'll ever succeed is almost zero. Almost zero. Right? And this is one of those you could try until the end of the universe and never succeed sorts of probabilities. Right? But there is some measurable probability, right, that the same quantum behaviors that the single electron had could happen to a larger scale object like a person. right? But like I was saying, if you think about it as the the more massive something is, the more effect it has on the probabilities around it, right? When you take two macro scale objects like a person and a wall, right, they they both they both have a large influence on the probabilities around them, right? So the wall, because it has so many atoms in it, right, will have a strong tendency to keep all of its atoms and to stay a wall, right? Once they're connected together into a solid object, right? And I mean that in the normal sense of a solid object, right? All of those particles are interacting with each other all of the time and influencing each other, so they have a strong tendency to stay together as a solid object. That's why solids are solid. Humans are kind of the same way, right? We like to think ourselves as a single connected thing. Oh, and that's a topic to go in this series. Yeah, are humans a single organism? How much of you is you? And this is another one of those questions that I'm proposing because it doesn't have a right answer. Right? I'm not going to tell you what the right answer is here because there is no right answer for multiple reasons. Because there are parts of you that are hard to classify, parts of you that are not alive, right? We're pretty confident that our hair follicles are part of us, right? Because they're living cells with our genetic code. But what about your actual hair? Right? Hair is made out of keratin. Right? It's a single protein repeated over and over again. It doesn't replicate. It has no moving parts. It's not alive. Are the parts of you that are not alive still part of you? Maybe, maybe not. On the other hand, right, we have a host of mostly bacteria that live in our guts, right? We have a pretty strong symbiotic relationship with them. Assuming you've got the right ones, they make your life significantly better. Right? You feed them, they provide you. Most of them don't really provide us with nutrients, but they help with chemical signaling, and they also fight off bad bacteria by using up all the available resources. Right? So our good bacteria eat all the food, and there's none left for the bad bacteria. Right? Which, in some sense, makes them part of our immune system. They're protecting us, but they're alive, and they have different genetic code. So they're not part of us, but they're kind of part of us. It's weird. You can consider them completely separate organisms, but they tend to be pretty tailored to the individual. The stuff that's in my digestive tract, my various microorganisms, are not necessarily very similar to yours. They tend to be custom based on our life cycle or our lifestyle. So there's a sense in which they're part of us. And if you say they're not part of us, then what about our mitochondria? Best current theory is that mitochondria didn't used to be part of whatever organism eventually evolved into us. Mitochondria are very old. So it's not like humans were around in the time before mitochondria. Probably organisms at that time were single-celled, a handful of cells at most. Our best guess is that this is a case where some single-celled organism ate the ancestor of the mitochondria. That the mitochondria's ancestor was swimming around in the primordial oceans by itself, and that the ancestor organism that eventually became like all the animals on Earth. So far as I know, all animals have mitochondria. I believe plants do too. I'm not sure about the other kingdoms. I'm not sure whether mitochondria moved in, for instance, before fungi split off or before protists split off. That's a look-upable answer, though. So the answer is most monorins, and the monorins are the single-cell prokaryotic organisms. Those with one cell, and I believe prokaryotic is no nucleus. Yeah, so any of the single-celled ones that don't have a nucleus probably don't have mitochondria. It seems like most of the monorins, the eukaryotes, in other words, they do have a nucleus. Most of those right. Are all the monorins prokaryotic? Yeah, sorry, these have been reclassified since I finished school, and I never really looked it up since because because so the monorins have been classified to be only the prokaryotes. What are single-cell eukaryotic organisms called? Okay, so the eukaryotes have been all shifted into protists. All right. When I was a kid, I was taught that everything with only a single cell was in the kingdom Monera. But it seems like we've started classifying things more strongly based on the contents of their cells rather than how many cells they have. So all the single-cell organisms with with all the single-celled organisms with complex structures. So, like we could consider the mitochondria a complex structure. But I think usually when we're talking about that, we're mostly thinking of the nucleus, right? Complex nucleus, but this is an interesting and potentially deep dive topic, but every topic is like that. And that's kind of the point of view that I want to promote, is that practically every topic has depth and nuance if you have the time to look into it. So we have apparently classified bacteria as insufficiently complex to be considered eukaryotes. And we're leaving all of them in the kingdom Monera. Yeah, that tracks with what I grew up in. It seems like yeast is the dividing line, because yeast is single-celled. Yeah, the yeast that we use to make bread or alcohol or pickles. The stuff we use for fermentation. It's single-celled. But it has sufficient complexity that we've moved it over into protist. Protista is the kingdom that has, well, basically anything that you would classify as slime. Like pond scum, yeast mixtures, slime molds. Yeah, if you look at it and go, that's slime, it's probably a protist. I don't know what the line between protists and fungus is. Right, because if you look at something and go, that's a mushroom, then it's a fungus. But there are some organisms that are really on the line between slime and mushroom. And fungus. So protists are mostly single-celled. And they behave in ways that confuse us. Fungi are usually multicellular. They're more complex, they're more, yes, solid. Right, the weird overlap is that there are some things that I would typically classify as protists, because all their cells are the same, but they kind of work together in a strange way. Right, that's why protists confuse us, is like slime mold looks like it's a multicellular organism. It looks like a complex life form. But it's actually not. It's a single kind of cell that has developed weird traits of working together. right? And you could kind of think about of us like that too, but the difference is that the more complex kingdoms, the fungi, the plants, and the animals, right? We have cells that are differentiated, right? Our skin cells are not the same as our muscle cells, right? They were developed, they came from the same cells, which are called stem cells, right? So when we're first conceived, we are made up of stem cells, which have the ability to differentiate into all the other kinds of cells. Right, but protists don't seem, so far as I know, to be doing that. They seem to yeah, like mold is mostly just one kind of cell, except for maybe it has strange behaviors when it goes to let off spores. Like molds let off spores the way that mushrooms do. Right, but they're individual cells that are working together as opposed to individual cells that are part of a larger organism. That's a really unclear line. Where do they stop being single cells with emergent group behavior and start being a single organism with multiple cells? I mean, I guess you could consider the line if you put them in a bucket and stirred them up, would they still work afterwards? Right? Because most, like, yeast are pretty simple. They don't work together very much, but the slime molds have some really complicated behavior, relatively speaking. But if you took a bunch of slime mold, stirred it up, most of the cells would still be alive, I guess, and they would still act like slime mold, right? They would settle back down and start doing their moldy little thing in the end. On the other hand, if you stir up a fungus or a plant or an animal, side note, I do not condone the stirring up of animals, especially not while they're alive. Right? If you stir any of those up while they're alive and rearrange their cells, those cells are pretty much all gonna die. So I guess that's really where the line is whether you could mix up all their cells and still have a functional living set of cells afterwards. Right? And anything with a differentiated biology is not going to fit that. Like I said earlier, our skin cells and our muscle cells are very different, and if you start swapping them around, you're in big trouble. Yeah, but if you took a bunch of slime mold cells that were working together and you mix them all up, they would still be alive and they would pretty quickly start behaving the way they normally do again. There are three types of protists: algae, protozoans, and molds. Assume that slime molds are molds. Protozoans are the ones that swim around on their own, like amoebas, or I forget, maybe liver flukes. I think malaria might be protozoa. Too complicated to be bacteria. Not complicated enough to be fungus, plants, or animals, which would push them into protist. They don't act like algae or mold, so I guess that would put them into protozoa. Let's see. Flagellata, Ciliophora, Amoebozoa, and Sporozoa are the four types of the protozoans. So it seems like a couple of those may have been renamed. Yeah, I'm going down this rabbit hole. That one looks like a mind flare. Let's see. This one in the top right is the one that I think looks like a mind flare. So, Giardia. It's a flagellate protozoan parasite. Oh, this is the one of the ones that's one of the ones that causes stomach issues, shall we say, because it gets into your digestive system and messes everything up. And then when it comes back out, if it gets into the water and somebody else drinks it, that's how it does its life cycle. Yeah, there's actually quite a few of those. They're generally all bad for you. Apparently, classification of the protozoa taxon. Its history is rife with people arguing. And it's mostly people discovering new things versus people who don't want to change the way they do things again and again and again. That's one of the rough sides of being a scientist is every experiment you run, you risk discovering something that means you have to rename everything. and then everybody has to learn the new names and everybody's annoyed. And it's good, right? It makes us more correct. Right? So protozoa are not, I mean, originally they were classified as animals because of their complex behaviors. They're not really related to animals like any more than they're related to plants or fungus. So it wasn't a good classification. It was simple though. Those were the days when we had plants and we had animals and just kind of dumped everything into one of those two groups. Yeah, and there's malaria. Plasmodium falciparum, a malaria parasite. It's a protist, and one that's bad for you. Because it destroys your blood. I think it damages your liver too. Back to the original question of uh, where are mitochondria from? Turns out protists have some of the most variety of mitochondria. It's interesting. Yeah, so the current theory seems to be that mitochondria started out as bacteria. Uh, a bacteria that managed to develop in such a way that it could get inside your cells and not kill the cells. Theory out there that the original mitochondria might have actually given the cells that they moved into some photosynthesis support. So that's kind of interesting. Although it seems like they basically all lost that ability now. Honestly, photosynthesis wouldn't do us that much good. Photosynthesis requires surface area to be effective. And we're all kind of round and squishy. Even if we're out in direct sunlight, we can't point enough of ourselves at the sun to really be useful. Right, that's why trees do the whole leaf thing where they stick their branches out as far as they can and then have big flat leaves that stick out off the ends of the branches. It's a surface area game. Phytoplankton get around this by being single-celled, so they get their surface area fixed by being numerous rather than being large. Right, so each phytoplankton is just efficient enough that its single cell is good enough. That's really the base requirement to be a photosynthetic organism is you need to produce enough energy. Each cell needs to produce enough energy to keep itself alive. Otherwise, you can't develop specialist cells, right? So trees have the leaves that produce more energy than the cells in the leaves need, and they transfer the rest of that energy to the rest of the tree. The trade-off is that the rest of the tree gets tall and spreads out so that the leaves have more opportunity to catch sunlight. Whereas for phytoplankton, it's every cell for themselves. Yeah, the other problem is that photosynthesis creates damaging oxygen radicals. So if you've ever heard commercials for has the most antioxidants, right? Antioxidants bind onto oxidative radicals and keep them from damaging your cells. An oxidative radical is any molecule that steals electrons. And if those electrons are part of your DNA, then that's bad. The DNA needs all of its electrons, and it needs them to stay in the same place. So that's why oxidative radicals are bad for you, right? That's how they help cause cancer for the most part, right? They increase your risk of cancer by stealing electrons from the pieces of you that need their electrons to stay put. And your cells will try to repair DNA if that happens, but if the repair goes wrong, well, if the repair goes wrong, then your cells will try to destroy it. But if the destruction goes wrong, then, I mean, generally still nothing happens, but every once in a while, if the repair goes wrong and the destruction goes wrong, and it's not something that is fatal for the cell, sometimes everything goes wrong in just the right way. And that's one way to get cancer, and that's how oxidative chemicals contribute to cancer. Kind of a similar mechanism for how radiation causes cancer, except in that case it's not a chemical that's going through and stealing your electrons. It's a single highly energetic particle, like a photon or an electron or a proton or a neutron, right? So a single highly energetic subatomic particle goes blasting through you, ping-ponging off of all of your cells, and sometimes that hits your DNA. There's actually two mechanisms there. It can hit the electrons in your DNA and cause damage that way. But sometimes it has enough energy that instead of just causing a little bit of damage, sometimes it'll split the strand entirely. Depends on how much energy it has, right? Because you got to remember, the electrons are the things that hold these long chains of proteins together. If you remove one, right, then you can get a kink, or sometimes you'll even get a split. If you remove a whole bunch of them, you can break the chain in half. And that's also bad. Anything that removes the connections and makes them reconnect wrongly is bad. Yeah, whether it's chemicals stealing the electrons or whether it's highly energetic particles like ping-ponging and knocking them off. Those are both bad. Also, sometimes radiation will hit a molecule and knock its electrons off, and then that molecule will become an oxidative molecule. And so sometimes even if the radiation doesn't directly hit the DNA, it'll create an oxidative radical, and then that will damage the DNA, right? So even indirect hits are not good. I've always kind of wondered what the effects of having too many electrons would be. Right? Like when people play with Van de Graaff generators, those are the things that make your hair stand on end and shock you if you touch other people. It's just a giant static shock machine, right? They're doing that by giving you a whole bunch of extra electrons. Or alternatively, taking away a whole bunch of electrons. Right? I mean, really, all it is just a belt on a motor with a brush at the bottom. There's a brush at the bottom and a brush at the top, and one of them takes electrons from one side and puts it on the belt, and the other brush takes the electrons from the belt and puts it on the other side. So it's just moving a bunch of electrons from one side to the other to make the two sides have a big charge. And that's why it shocks you when you touch it. It's because that's all the electrons jumping back to where they came from. I don't actually remember which way most Van der Graaf generators go, whether they give you more electrons or whether they take away your electrons. But I've always kind of wondered if you... Like, I guess you could run an experiment, get a bunch of mice or rats or... And you put the Van der Graaf generator between them so that one side has a lot of extra electrons and the other side has a lot of missing electrons. Right? Because so far as I know, there's no big effect to being electrically charged, at least for a short period of time. But I wonder if anybody's ever tested if there are long-term effects. There are long-term effects to being injured by electricity, but that's not the same thing. Yeah, I don't want to know about being shocked, right? Having electricity flowing through you is bad. Everybody agrees that's bad. Don't do that. Don't send electricity through your body. But that's a function of the charge carriers, in this case the electrons, moving through your body, right? And most of the damage there is done by heat, because when a charge carrier moves through a substance, it heats up. And that's really bad, to burn the insides of your body. Exposure to static electric fields, that's closer. So this is an interesting study. It's basically when people go near high voltage electric power lines and our hair stands up because we can feel the electric field around the lines, we seem to find it annoying. But they have not found anything that suggests it's harmful. Right. Let's see, here's a study for, instead of static fields, for alternating current fields. Okay, so that's interesting. Low frequency alternating current electric fields, where the current is not part of the fields, but the fields alternating and the current alternating are part of the same system. So if the fields have a frequency where they alternate, that does seem to be bad for us, because it seems like that the switching back and forth can induce currents. If you put something conductive in an alternating field, you'll get an alternating current in that conductive substance. And we're a little bit conductive on the inside because, like, we have blood, which is conductive, and like, our blood is filled with salt water, and our cells are filled with salt water. Salt water is conductive. And apparently there are laws saying low frequency fields have to be below a certain strength. And that makes sense. They don't actually give a frequency range. Yeah. Powerful low frequency fields are bad for your blood, and they're bad for your nerves in particular. Seems like the fields need to be relatively strong, though. 0.3 microtesla. It doesn't sound like a lot, but 1 Tesla is a fairly strong magnetic field, so 3 parts in 10,000 of a Tesla is still a reasonably strong field. Which is why we've got no evidence that cell phones are harmful, because they're just not that powerful. That's an interesting result, and something I didn't know. I was under the impression that electric fields could be bad for you, because that was something my mom told me as a kid. Right? She said, stay away from the television if you get too close to the television. Right? Although televisions today do not create electric fields that are nearly as strong as the ones as when I was a kid. Also, when I was a kid, the cathode ray tube televisions were still kicking around. So, the other problem with those is, what a cathode ray tube is it's basically a gun, an electron gun. It uses electronics to create free electrons, and then uses magnets to accelerate those electrons like a railgun. Right, and it fires those electrons into a glass screen covered in phosphorus, and then the phosphorus lights up. Right, The electron hits phosphorus, phosphorus starts to glow. And that's how televisions used to work. But there's also the non-zero chance that those high-speed electrons might not hit the phosphorus. And they might not get stopped by the glass. And if they didn't, then now you have high-energy electrons flying around your living room. For the record, electrons do not go very far before they lose all their energy in air. But that's why you should not sit right up against a cathode ray tube television. It's a combination of, apparently, the electric fields and the possibility of high-energy electrons. But yeah, I mean, high-energy electrons are not super dangerous. Right, like if you stick your arm in an electron beam, you're going to get different results depending on whether or not you're wearing long sleeves. Some of them will still get through your sleeves, but normal clothing will block most electrons because electrons have a high charge and they interact with all the things around them very strongly. That's why everybody's always talking about gamma radiation. Gamma radiation is the dangerous one. Because gamma radiation is made out of light, and light is not charged, so it goes through stuff easily. Different frequencies of light go through different stuff. Right? That's why some colors are reflected and some are absorbed, depending on the material. When we're talking about gamma radiation, we're talking about like we usually start talking about frequencies when we're outside the visible range, right? But we're talking about a color that's much, much bluer than blue, right? Way past the blue end of the spectrum, right? We go blue and then we go violet and then we go ultraviolet. You know how the middle of the ultraviolet is where things start to get bad for us, right? So ultraviolet B starts to damage our skin, but it's also the wavelength that lets us produce vitamin D. So there's some trade-off there, right? Getting some sunlight, right, produces vitamin D, which is good for you, and the benefit may outweigh the risk of cell damage from UVB. UVC, on the other hand, which is even more violet than the other ultraviolets, right? So where ultraviolet means we're past violet, right? And C is now we're on the third step past violet. That's super bad for you, right? That'll give you a sunburn right away, and that's one of the things we need the ozone layer for. It's because ozone absorbs ultraviolet C radiation. So having an ozone is nice because it means that down here on the surface, we mostly only get ultraviolet A and B, right? So we can get our vitamin D and not get horrific sunburns in the process. Although you still get a sunburn if you stay out too long, because some of it gets through. Right, and that's what sunburns are. Sunburns is the light getting in and damaging your cells. And then up above ultraviolet, we have X-rays. Right. The more powerful a thing gets, the better it tends to be at going through otherwise seemingly solid objects. Right. So like purple light bounces off of our clothes and our skin. Right. Whereas ultraviolet A, right, it gets into our skin a little bit. Right, it's not super damaging, so we're not usually too worried about A. Ultraviolet B can get into our skin, which is why we have sunscreen, right? It's a chemical that's designed to absorb and or reflect ultraviolet B light, right? So that blocks the B, and we also want it to block the C. Right? So if you're looking at sunscreens and you see some of them say UVA this, UVB this, UVC this, right? You super want to block all of the UVC. And you mostly want to block almost all of the UVB. And if you can, it's nice to block most of the UVA. UVA is the least harmful because it penetrates the least. It interacts the least with the parts of our bodies that are alive. Whereas once you're past ultraviolet and you're sweeping up through at the X-ray range, right? Middle to high level X-rays can go right through your body. Right? We use them for medical imaging because they go through the squishy parts of your body, but they interact a lot with your bones. Probably the calcium in your bones. I'm not totally sure. It's just a guess. But because our bones are solid and full of metal, presumably, right? Something about our bones. I'm not going to commit to something I don't actually know. Something about our bones interacts with X-rays more than, like, significantly more than our blood and our muscles. And that's why when we shoot somebody with a bunch of X-rays, most of them go right through, but the ones that hit the bones don't. And that's why the skeletons in an X-ray image have the colors interpreted, right? The bones are dark because the bones blocked the light. It's like if you drew a picture of the skeleton on like a clear window and then shined a flashlight through it. The picture of the skeleton would show up as a shadow. So that's what's happening in our X-rays. Is our bones are showing up as shadows on the X-ray film, which is basically the same as photograph film. Same idea as, I mean, I don't know that really anybody uses cameras with film in them anymore. Everybody's digital these days. And I'm under the impression that some X-rays have gone digital too. Like instead of using actual film to catch the X-rays, we now have basically digital cameras that are tuned to pick up X-rays instead of red, green, and blue. So it really is just a digital camera and a really bright spotlight. It's just a much higher frequency. Like the color is way past our ability to see it. X-rays don't interact with our eyes basically at all. On the other hand, when they do interact, they have a lot of energy, so they can damage things. That's why you should not, live in an X-ray chamber. That's also why the X-ray technicians always run and hide behind a big lead wall before they take the X-ray photo. Right? It's because it's bad for you. If you're the person who's hurt, then the benefit of knowing what's broken is more important than the small amount of damage that the X-rays will do to you. And they do some damage. Like there is, like every time you get an X-ray, you are doing some damage. Right? And hopefully your body will always repair that damage successfully, or at least destroy the affected cells if repair fails. But an X-ray tech takes X-rays like all day, every day, right? So they don't want to be in the room because A, there's no benefit to them being in the room, right? They don't need to get hit with the X-rays. And if they did, they would take a little bit of damage all day, every day, and that adds up in a way that's not good. So if you've ever gotten an X-ray and seen the X-ray tech go, okay, now don't move, and then run out of the room to take the picture. That's why. Yes, you did take a little bit of damage. Not enough, probably, to affect your life. But they ran away because if they took that much damage with every X-ray, it probably would affect their lives. So they try to avoid taking any damage. Same with people who work at nuclear power plants. Nuclear engineers. Well, one of the things that nuclear engineers do, and X-ray techs do this too, is they wear little meters, usually on their belts, that keep track of how many high energy incidents they've had. So it keeps track of how much radiation they've been hit with, and they all have you get a monthly report that says this is how much radiation you've been hit with this month. You are above or below. You are above or below the average radiation dosage received by, a typical American. And if it's above, then your manager will call you and be like, stay further away from the reactor. Getting too much radiation. And then you do, because you don't want to get too much radiation. And you really can't tell. Right? You can walk right past a nuclear reactor, with the caveat that you're on the other side of the shields. Right. So reactors have shields around them for a reason, right? But the area right outside the shields does have more radiation than areas far away from the shields. Right. But you could, at least for all the reactors I've ever met, I've heard horror stories about some early reactors and some reactors in other countries. But in the United States, you could walk right up to the reactor's shield, the outside of the reactor compartment. You could lean right against it and you wouldn't feel anything. Even a dangerous dose that is going to hurt you, you wouldn't feel it right away. Usually you don't, even in big disasters, feel like there have been a couple of disasters in Russia. Some of the people that were responding to the Chernobyl disaster, right, they didn't get sick right away. They got sick a couple of days later. Unfortunately, by the time you get sick, chances are you've already taken a dose that's fatal. Right, because you can't feel it when you're getting hit. That's why radiation is dangerous, because you don't feel it when you get hit, right? Well, it's the same for sunburns, right? You don't. By the time you've developed the sunburn, it's already too late, right? The sunburn that you develop in the afternoon is from the sunlight that you got in the morning and lunchtime, right? And the sunburn that you get in the evening is from the sun exposure that you got in the afternoon. So by the time your skin turns red and starts to hurt, it's too late. You've already gotten zapped. It's the same problem on a larger scale for major nuclear accidents. Thankfully, on the whole, the history of nuclear power plants is pretty safe, with the exception of Chernobyl was a mess. It was a mess caused by bad policy. Operators were doing something they knew wasn't safe, and they were doing it because they were scared they were going to get fired if they delayed the tests that were going on. That did not work out for them. Fukushima, I think, is another one that comes up in people's minds. That was kind of a freak accident. There's only so much you can do to safeguard against a tsunami. Tidal waves are just super destructive that way. The issue there was that the tidal wave did so much damage that it knocked out the normal systems, but it also knocked out all of the emergency systems. Right, so things started to get damaged there, and they emergency pumped into the radioactive stuff into the holding tanks, the emergency holding tanks. They had those. That was it was a good plan. Except those got damaged too, so there were leaks. That's why Fukushima was such a problem. Was that everything got damaged all at once, and even then, when we go to measure the actual effect, right, the safety measures that were in place mostly worked. The actual effects were not as bad as a typical member of the public thinks. It's kind of the same way with 3 Mile Island. 3 Mile Island was another one that was caused by operators not making good decisions. In that case, so far as I know, there was no external pressure. It's just the late night shift made a stupid decision. Like they had a brain fart, and it was not good. And so far as I know, there was no leak to the environment. But all of the problems at 3 Mile Island were contained within the secondary containment. That's another thing that a lot of people don't really realize about nuclear power plants, is that modern nuclear power plants have multiple levels of containment. Right? There's the primary containment, which is right around the reactor. Then usually there's a secondary containment, which is around the power generating facility as a whole. And then usually these days there's even a tertiary containment, right? There's a 3-level containment. The third level is not like walls and tanks and stuff. It's basically like a fence and a moat around the facility to make sure it's as much to keep people out as it is to keep radiation in. But yeah, most of these facilities are set up in such a way so that even if something somehow gets out of the secondary containment, right, and spills on the ground, it's going to sit on concrete and not sink into the groundwater. Right, the secondary containment is usually a building. Power plants are usually inside. So usually you have like a reactor compartment, and then you have, yeah. And often the reactor vessel itself, is usually A, made of metal and or concrete, and B, filled with water, right? Because we use the water to collect the heat that we turn into steam to turn the turbines to make the electricity, right? And water is good at blocking radiation, which is a nice bonus on why we use it, right? Because it's easy to put extra water in because it's cheap. It makes good shielding. Right, so it's layered defense. Yeah, so a typical modern reactor is very safe. Like, every time something goes wrong, we add new automation, we add new sensors and safeguards, right? So these days we not only have humans that can turn things off in an emergency, we also have computers that can turn things off in an emergency. Historically, we're very reluctant to let the computers turn things on, right? Turning nuclear reactors on is something that's usually very carefully monitored, right? You usually have a whole bunch of people sitting there watching it to make sure that nobody makes any mistakes. Generally speaking, we're totally okay with letting the computers go. This is an emergency. We should turn everything off. Right? That's a perfectly acceptable safeguard, because a lot of times a computer will notice something has gone wrong faster than a human will notice it. That's also why we have smoke alarms. when I say computer in this sense, I mean that very loosely. These are very simple electronic circuits for the most part. Your smoke detectors typically just have a little radiation emitter inside of them and a little radiation detector. And if smoke gets into the smoke detector and gets between the emitter and the detector says, "Oh no, something is blocking the radiation from my little radiation source. I should sound an alarm." And then it sounds an alarm. That's why your smoke detector goes off before you can see visible smoke, is because it can detect very small amounts of smoke in the atmosphere. And same thing with power plants. So we have detectors that say, "Oh no, something is getting too hot. We should turn the reactor that's making it hot off." Or, "Oh no, there's too much radiation. Something is producing too much radiation. We should turn the radiation off," and turns off the reactor. Or, "Oh no, the operators are trying to change the power level too fast. And history teaches us that that can lead to problems. So we're going to not let them turn the power up anymore. And it'll either cut the signal that lets them turn the power up, or it'll turn the reactor off." It kind of depends on how bad the error is. And also on who was designing the system. I don't know what a typical system does these days. Yeah, but there are lots of little detectors that in a nuclear power plant whose only job is to sit there and go, "Oh no, we should turn the reactor off," and then turn the reactor off. And so far as I know, that all went right at Fukushima. Right? That all of that stuff went well. The problem is that nuclear reactors, even after you turn them off, are still hot. Right? And they continue to get hotter for a while after you turn them off. Right? That's something that's unintuitive, right? Because when you put out a regular fire, it can still be hot, right? But it doesn't keep getting hotter. Right? When you flip the switch on a reactor to off, assuming your reactor has a switch that says off, it's not necessarily what it's called, but the reaction doesn't stop right away. That the best you can do is you can flip a switch that says start slowing down. Right? It's more equivalent to hitting the brakes on a train, right, than it is to putting out a fire. Right? When you hit the brakes on a train, the train starts to slow down, but it is still moving forward, right? So you need to hit the brakes while you still have enough track in front of you for the train to slow down. And that's what went wrong at Fukushima, was when the tsunami hit, right, everything was off. Right? The reactor was shut down. Right? But the equivalent of the brakes is the cooling water that goes through the plant to keep things cooled. And then when the tsunami hit, that was what failed, was the cooling water got knocked out. Both the main power source for the pumps and then the backup generators got knocked out as well. Right? So the pumps for the cooling water got knocked out, which meant that like the chain reaction, right, the train in our analogy, was still moving forward. Right? But now we no longer had the cooling water laying tracks down in front of the train, so all of the water that it had was all the water that it was going to get, right? So that water started heating up, right? And eventually, when you heat up water like that, it starts to boil, and then you're in trouble. The water that's going to go through the generators, the turbines for the generators to make electricity, you want that water to boil. The water that's going to go through the reactor to keep the fuel cool, you do not want that water to boil. That's bad. Right. Now, I don't know if Fukushima even actually melted down. So a meltdown is a different thing. A meltdown is when the fuel overheats and starts to melt, and the fuel starts to get released into the cooling water. So that's a meltdown, right? I don't know if that happened. That, so far as I know, did. Okay, no, now that I think about it, I'm not sure whether or not that happened at 3 Mile Island either. Right? But the meltdown and the release are separate things, right? So the meltdown is when the fuel starts to get released into the cooling water. The problem is that often when that happens, the cooling water is already boiling, right? So it's blowing its emergency relief valves, right? So those are two different things. The water that goes through the reactor is not generally super radioactive to start out with. So if you blow the emergency release, like I said, in a normal modern reactor, that just goes inside of the containment building. So it's not that radioactive to start out with, and it doesn't get out into the environment. The problem is when things get really out of control and the fuel starts melting and getting into the water, and the water is getting released. Right now, that water is pretty radioactive, and if you're not in too much trouble, right, that water is still going to stay in the containment building. Right, so now you have a mess that you need to clean up in the containment building, but it's still not out in the environment. Yeah, Fukushima's problem was that the tanks that they were emergency pumping the water into that were supposed to contain it, some of them were damaged. At least I think that's what I read in the news. Right, so that's how it leaked there. Chernobyl, on the other hand, was a completely different issue. It's because they were using their water to collect the heat to turn into steam, like most reactors do these days, but you know how I said we surround our reactors with water to bounce the radiation back into the reactor? They were using graphite to do that instead. And there's advantages and disadvantages to both systems. One of the disadvantages to graphite is that it's flammable. So when they overheated, the graphite that they had surrounding the tank caught on fire. So now we had radiation going everywhere, and it was radioactive material that was also on fire. And water is relatively easy to contain compared to fire. That's why Chernobyl turned into such a freaking mess. And it's why most designers these days are hesitant to use graphite to surround their reactors with, because it makes people really uncomfortable. Yeah, that's one of the nice things about water, is it can absorb. Also, it can absorb a lot more heat than graphite does. And even when it does absorb a lot of heat, it turns into steam instead of smoke. Right. The thing is that steam, when it escapes, cools down quickly and turns back into water. Right, and then it falls on the floor. Smoke doesn't do that. Right, smoke fills up the building and stays suspended in the air for a long time, so it gets out through like windows and air conditioning, or really any gap. Of course, I'm under the impression that the Chernobyl incident went on long enough that it managed to destroy most of its containment buildings, so by the end it was really not contained at all. They just resorted to driving in dump trucks and cement mixers and dumping thousands and thousands and thousands of tons of sand and concrete on top of it just to get it to stop burning. And by burning, I mean like it was a regular fire, right? The heat was coming from the nuclear fuel, right? But the stuff that was burning was all of the stuff that was in the power plant, right? And you can't put that out with a fire hose because as soon as you turn the water off, it'll light back on fire because it's still hot because of the nuclear fuel underneath. So they gave up trying to cool it down and switched to just putting a giant concrete lid on top of it. Which, I mean, mostly worked. A lot of people were very sick afterwards. Like all the people driving those trucks and trying to put all the people trying to put the fires out. It was not good for them. But it did more or less work. The fires eventually did go out, and we stopped pouring radioactive smoke into the atmosphere. Which is good, because even the smoke that did get out, spread across basically the entire planet. That's one of the issues with smoke, is that if you produce enough of it, it goes all over the place. Same with the wildfire issues that we have. Like when we have big old wildfires, right? You can smell the smoke from thousands of miles away. In this case, there was a lot less smoke than that. It's just that the effects of it were much worse. So we had alarms much farther away. Because every little bit of radiation is bad. Well, bad if it gets to you. It's good if it heats up the water in the power plant and produces electricity. That's good. Gets absorbed. Doesn't escape. Doesn't hurt anybody. Produces electricity. That's good. It's only bad if it gets to you. That'll be my 2024 quote. On the flip side, the whole keeps reducing heat even after you turn it off is why we've been chasing, one of the reasons why we've been chasing after fusion power for so long, is because a fusion reaction sputters out almost right away when you stop providing fuel, right? In a fission reaction, all of the fuel in the reactor, more or less all of it, is reacting a little bit all the time. In a fusion reactor, only the fuel that's going into the reactor is reacting. Right? The stuff in the storage tank out back is mostly inert. It just sits there. Typically, those fuels are either hydrogen with extra neutrons, which is a little bit radioactive, so it is bad for you, but just don't breathe it in, and you'll be okay mostly. Don't like live right next to the tank. Not that anybody would. And same issue for some of the lithium fuels. Like some isotopes of lithium are radioactive, but again, it's as long as it's sitting in its storage tank, it's not doing anything. Both hydrogen and lithium can be a little bit fiery when you mix them with oxygen. So that's something you need to avoid. You need to make sure that those tanks are set up so that they don't ever get regular air in them. The hydrogen tanks should only have hydrogen. The lithium tanks kind of depends on how you're storing it. But right, if you're going to pressurize those tanks with gas, it needs to not have oxygen in it. Lithium's usually a solid, is kind of the issue there. But you can't store it under a vacuum, because if you store it under a vacuum and there's a leak, it'll suck air into the tank, which you don't want. So far as I know, lithium doesn't react with nitrogen or argon gases, so you just fill the tank with those, and then if there's a leak, the non-reactive gas will keep the reactive gas out. But the actual nuclear reaction is not happening in those tanks, right? That's only happening in the reactor, because a fusion reaction requires millions of degrees. Right? It has to be extremely hot. And the tanks are at room temperature. So the only place is inside the reactor. It's the only place that's hot. Probably the only place definitely the only places on Earth are inside of nuclear reactors of one sort or another. The only other place that even sustains that sort of reaction is the sun, and the sun is cheating to do it. So part of the sun that is reacting is technically not hot enough to sustain the reaction. It's cheating because it's big. So the idea to get a sustained reaction is that some of the particles that launch out from one reaction hit more fuel and start the next reaction. Right? So in our tiny reactors, we have to get it up to a certain temperature, because we need the next reaction to happen while those particles are still in the reactor. Right? So we need to make those reactions easier. The sun doesn't have that problem, because if the particle in the middle of the sun misses all of the nearby fuel, it still has to make it all the way out of the sun, which is a long, long way. And there are a lot more fuel particles in between the middle of the sun and the outside of the sun. So most of those high energy particles, are going to hit something on the way out. So the sun does not need to be as hot, because it's big. That's why I say it's cheating, right? Because we're forcing the reaction to happen by making it really hot, and the sun is just kind of letting the reaction happen by virtue of being very large. Don't get me wrong, though, the middle of the sun is very hot. Like, the middle of the sun is hot enough to start the reaction on its own. It's just it gets bonus efficiency because it sparks coincidental reactions as the energy moves from the middle towards the outside. Yeah, humans wish we could get some of that bonus efficiency, right? Because we've been able to start a fusion reaction for a long time, right? And we've been struggling for decades and decades and decades to make it efficient enough to keep it going, right? Because getting it started takes a lot of energy, and if you can't capture at least as much energy as you put in on the way out, then the reaction will stop. And it's just been in the last decade that we've gotten to the point where we can create a reaction that's big enough and efficient enough to get more energy out of it than what we used to start it. That's that seemed like an easy problem 70 years ago. Right? That's where the joke that fusion power is 30 years away and always will be comes from. It's the problem of getting it to the point where we get more energy out than we put in seems like such an easy problem. But it turns out it's really fiddly to get all the settings just right. Yeah, everybody who's been working on it has been saying, we've almost got this. We've almost got this. And they've been saying that for 7 decades now. But in the past decade, we actually have had reactions where we got more power out than we put in, which is, that's a good sign. And computers have gotten a lot better in the past couple of decades. So now we have computers that can measure the reactions better and create better records of what happened. And we can use those to create better mathematical models, better simulations of the reactions, which means that we can tune the settings much more precisely. Right? We can do running an experiment on a simulation is much, much faster than running an experiment in real life. So we can run many, many experiments with all sorts of different configurations, right? We can say, well, what if we built a new reactor that was shaped like this instead of like the one that we have? Right? Now, these days, we can simulate that new reactor reasonably well instead of needing to actually physically build a new reactor. At the end of the day, you do need, like, you run all of your simulations and you pick the best, 1 or 2 or 3. At the end of the day, you do need to actually build them and see if the simulations match up. And then you measure the results from the prototypes that you actually build. And you put that data back into the models so that you build new simulations that are more accurate. And then you do it again. And that cycle goes much faster than if we had to build a new building, do the tests by hand, and then figure out what went wrong by hand, and then build a new building by hand to try out the next version. With the computer models, we can skip a couple of versions with simulations. So in the time that it used to take us to do one build a new thing cycle and run all the tests and then start the next cycle, right? Now we can do, multiple cycles through simulations. So in the same amount of time, it's as if we had done 4 or 5 cycles or 7 or 10 cycles or however many cycles at the way that the people in the 70s had to do them. Right? And that's something that a lot of people are working on in general, is working out how to build better simulation structures simulation structures. Right. There are a lot of people that are interested in that from all sorts of different fields, right? Because that applies to anybody who builds anything, right? Being able to simulate your changes makes it much faster to figure out how to improve your things. That's electronics does that, computers and cell phones and your tablets, but also like cameras and all the different like bits and pieces that go in your self-driving cars, or the pieces that we use for airplanes, right? The instrumentation that goes into like chemistry labs, right? That measures things, right? all of those sorts of electronics. Everybody's always trying to improve the speed. You want the speed to go up, you want the precision and the accuracy to go up, and you want the power consumption to go down. Right? Those are the three main goals of everybody who works with electronics. It needs to be faster, it needs to be better, and it needs to be less expensive to run. Preferably, it also needs to be less expensive to build. So if you can trade out some expensive materials for not expensive materials, that's also good. That's going to get you a nice bonus in your paycheck. That's a little bit harder to simulate. Right? Because most simulations, it's a configuration that you're testing and not the actual materials that you're building stuff out of. That's its own branch of science, by the way. It's just like there are people who do nothing but, take a bunch of materials and search for the best materials for whatever given purpose they're researching. They run a totally different kind of simulation. I mean, it's kind of the same kind of simulation, but it's focused in a completely different direction. Right, so they're trying to predict which materials will be the best at the property they care about the most. So that's something you hear a lot about in things like solar power, right? So solar cells, right? One of the big issues with solar cells is that traditionally they require very pure silicon crystals to get the most efficient cells. And right now that's still mostly true. It's very expensive to grow pure silicon crystals. Right. And also some of the other ingredients required for a solar cell are very expensive. Electronics in general has a lithium problem. Right? Lithium is very expensive. There's not a lot of it. I mean, in the universe, there's plenty of it. In Earth, where we can get it and mine it out of the ground and refine it, there's not very much. So it's not that there's not a lot of it in the universe. It's that it's in places that are hard to get to for us. But that means for the electronics industry, that's very expensive. Because first you have to find it, then you have to mine it, and then you have to refine it, and then you have to store it because it's kind of reactive and it's hard to work with. Very expensive. So electronics. Well, that was odd. I just got a disconnect notice. Let me check. It's still online. Okay, seems like it's still online. So that's nice. That was weird. I wonder why I disconnected for a minute there. As I talked about, why lithium is problematic. Yeah. Lithium's problematic because it's expensive. Because it's hard to get. Right? So everybody's always looking for ways to get the same effect with materials that are easier to get. Silicon, the problem is not that it's hard to get. Silicon all over the place. Sand is made of silicon and oxygen. Right? So anywhere that has sand or sandstone has plenty of silicon. The issue with silicon is that it needs to be refined to separate it from all the other things that are in sand. Dirt. Dirt is mostly carbon. We don't want carbon. We want just the silicon. Alright, so we need to refine it to get rid of everything else. Then, we need to grow it into relatively large, extremely pure crystals. And if you've ever tried to make, like, sugar candy, you know that controlling crystals is a pain in the butt, right? Whether you've made the kind of hard candy where you're trying to avoid crystals, or whether you've made rock candy where you were trying to grow the crystals, right? Getting good crystals can be a pain, especially on the sort of scale that Earth currently uses silicon-based electronics at. Right? If we just needed a few, right, that wouldn't be a big issue. Because we use so much that growing that much of it is really, really a pain. So everybody's always looking for materials that are easier to get. Um, yeah, as far as we can tell, a lot of electronics really does require crystals of some sort or another. So perovskites have been in the news lately. I forget exactly what they're crystals of. I want to say like sulfur and lead, maybe. Sulfur and lead are easier to get than either lithium or high purity silicon. Um, so as long as the crystallization technique isn't too bad, right? Perovskites have a lot of promise. The issue is they're a lot cheaper, but we're still working on finding exactly what combination of materials makes a crystal that performs as well. So we've reached a point where people are not willing to pay for perovskites even if they cost less because they don't last very long. That's the main issue. Also, they don't work as well, right? For solar panels, right? They do not turn as much of the sunlight into electricity. At least last I checked, the silicon-based solar cells turn more of the sunlight that hits them into electricity, so they're more efficient, and they also last longer because the perovskites, at least the ones that I read about, seem to break down relatively quickly. We want something that lasts for about 20 years, and we want it to collect about 20% of the sunlight. More is better, right? 20-ish% is commercially viable, right? Where it's 20% is viable with a silicon-based solar array, right? Where if you live somewhere that gets a lot of sunlight, it will pay for itself eventually. Like it will pay for itself before it breaks down. That's where the tipping point is. Everybody will buy solar panels as soon as we have a pretty good guarantee that those solar panels will make more money than they cost. Like if I said, hey, here's this thing, you pay me, $1,000 up front, and over the course of 5 years, it'll make you $5,000. And it was pretty guaranteed, 95% guaranteed. Unless something goes totally wrong, like if the thing breaks early, right, then it would be under warranty, right? So you can get me to refund you. Right. So if you were basically guaranteed that you were going to make $4,000 on that over the next 5 years, right? That's a times five, right? That's a really good return rate. Like the stock market is not doing anywhere near that well. That's a good investment. You would, for however many thousands of dollars you could spare, that's how many panels you would buy. Right? To the limit of how much land you have to put them on. That's one of the other issues that kind of comes up with solar power is right, if you're going to put it on top of your house, you're limited by how big the roof is. So if that's your limitation, then you want something that's more efficient, that'll do more with the same amount of space. As long as the price goes up more slowly, then the gains that you get from it. That's why everybody's not running out and switching to solar power right now, especially in places that don't get a lot of sunlight. It's that the economics are not quite there yet to guarantee that they're going to make their money back. That's what most people want. Like, there's a segment of the population, and not a small one. There's a fair number of people who are willing to pay a little bit more to switch to solar from an electricity source that's harmful or more harmful, right? Solar has some harm. We really need to get to the point where we're better at recycling old panels. And the other major one is we need to, when we're creating the panels in the first place, some of those processes use chemicals that are dangerous. So we need to make sure that those are being broken down and preferably turned back into something useful. Preferably you want to recycle chemicals in the processing as well as the products. That's something that doesn't get talked about a lot when we talk about recycling. Is we mostly talk about recycled products, which is kind of iffy depending on what they are. Metal and glass are relatively easy to recycle. Recycling plastic products doesn't work very well. Right, if we're being honest, the second generation products are lower quality. Right, they're not as good as the first generation products. So often with plastic, you can only recycle it once or twice at most. Right, so if I made a bottle completely out of recycled bottles, that new bottle would not be as good. Right, and if I made a bottle out of those second generation bottles, that third generation bottle would be even worse. Right, which is why metal and glass are preferable, because metal and glass they're very simple molecules. Right, glass is just a mixture of silicon and oxygen for the most part. We put other things in it to give the glass properties that we want, like pure silicate. Silicate is a silicon with 4 oxygen atoms. Pure silicate glass is super clear and very hard and doesn't dissolve particularly easily, those are mostly the properties that we want. It's not especially strong, right? It's pretty brittle, but almost all glass is brittle no matter what we do to it. The downside is that it's harder to make, right? You need to get it much, much hotter. Like pure silicate glass needs to be heated much hotter, which makes it much more expensive. So what we usually do is we add potassium to it. So it's called soda lime glass, right? So we add lime, which is lime is the primary component in most limestones. It's calcium carbonate, right? It's present in eggshells and seashells and limestone. Like limestone is mostly made of seashells that's been compressed. So you take that, you heat that up in a furnace, it pops off a carbon dioxide, and you're left with calcium oxide, which is also used for cement. Right? And that's a useful chemical. Not great for the environment due to the popping off the carbon dioxides to get it to react with stuff step. We're working on that. There are ways to mitigate that problem. They're coming along slowly, but they're moving. And the soda part is talking about I think it's usually talking about potassium hydroxide, which we get from ashes. So trees concentrate potassium from the environment. And I think that's the soda that they're talking about in soda lime glass is the potassium soda that you get from ashes. Right, so that's also kind of a mixed bag environmentally. Depends on I mean these days we get most of our potassium ash. We don't actually get it from ash anymore. We get our potassium salts from underground. We dig a well in an area that has lots of potassium salt in the ground, and then we pump water into it, let it dissolve the salt, and then suck the water back out. And then we let the water evaporate off and collect the salt. So mostly we don't collect potassium salts by burning down forests anymore. There was a time when that was the number one way, was you would cut down the trees and bring them to a factory and burn them to ash, and then you would collect the potassium hydroxide from the ash by mixing it with water, and then you would use the potassium hydroxide to do your chemical reactions. Yeah, that's expensive, and if you keep doing that, you run out of forests. So we decided collectively that that's not a great way to do it. I mean, in theory, we'll eventually run out of places that have high levels of potassium salts in the ground. Right, so mining will eventually become problematic. If we're doing a good job, by the time that happens, we will have figured out how to recover the potassium that we used for the other stuff. Right. But that's off track. The reason you add those to glass is because it lowers the melting point. That's the main thing, right? Lowering the melting point means that you can use less fuel to heat it up, and it gets much less viscous, less sticky, right? It becomes more liquidous, more like water and less like honey, which means that you can pour it and turn it into things more easily. The drawback is that soda lime glass is susceptible to acids. That's right. It's because of the new components that we put into it are susceptible to acids. So it does not make good chemistry lab equipment. Depending on how acidic your rain is where you live, it may or may not be good for windows. But that's like, it might not, it's totally fine for windows, at least, in the short term, so you won't notice anything within like a decade or two. But if it's constantly exposed to acid rain, then over the decades, that'll wear it out. Same thing with for plates and glasses, bowls, things like that, right? Some of the food that we eat is relatively acidic, but you don't leave it. Right? You don't pour lemon juice into your cup and then leave it for 2 years. Right? It'll wear out eventually. Yeah, because most of your cookware and your tableware is the glass stuff anyway, not the ceramic stuff. But most of the glass tableware and cookware is soda lime glass. Except for the stuff that's meant to go on the stovetop or in the oven, because one of the other things that soda lime glass is not good at is it's not good at changing temperature quickly. If you've ever seen somebody pour boiling water on their car door to try to unstick it when it's frozen and seen their window shattered, this is why. Glass does not like to be heated up and cooled down quickly. To fix that problem, instead of soda and lime, we add boron additives. Boron is just another element. The thing about the boron is that it changes the crystalline structure of the glass such that it's much more resilient to fast temperature changes. Also, since it doesn't have the soda and the lime, it's not as sensitive to being dissolved by chemistry components. So, borosilicate first saw its use in lanterns, like the kind used for lighting. One of the issues that prompted its introduction as like an actual product that people were buying and selling was emergency lanterns for railway signals. Right? They had an issue where, you needed to light the lantern, and the lantern would quickly heat up the lens. You needed a lens to focus the light so that the trains could see the signal. Right? But if you heated the lens up too fast, it would crack. Right? Which makes it not nearly as useful. And so the rail companies needed to change out these lenses quite frequently, and it was both a safety hazard and quite expensive. So when it was discovered that adding boron to glass made it more resilient to temperature changes, that was one of the first uses, was they started making lantern lenses out of it so that when they got hot, right, they wouldn't shatter. They were more expensive, but they lasted longer, so it was worth it in the long run. And that's also something we care about in chemistry, right? We want clear containers, right? Because we want to be able to see the chemical reaction. We also want to be able to set them on top of our hot plate or our burner. Right, so borosilicate glass is very popular as chemistry glass. Relatively immune to chemicals. It's pretty good at heating up and cooling down quickly, so you can set it on a heat source. Right, it's clear, so you can see the reaction. And the Pyrex brand got very famous for making chemistry glass. And they switched, they kind of converted that brand image over to making homewares. And they made borosilicate containers for use in the kitchen. So older Pyrex kitchenwares were safe to put directly on the stove top or in the oven, right? Because they were borosilicate and they could heat up. Unfortunately, I believe Pyrex has licensed their homewares brand, has licensed their brand out to a different company that has started making very similar looking products out of soda lime glass. So these days, if you find that you have a Pyrex container in your kitchen, you have to look at it very carefully and see whether it says okay for stovetop or don't use it for stovetop. And if you buy new Pyrex glass, it will not be good for your stovetop. So if you want something to use on your stovetop, you should search for borosilicate glass. And the piece that always makes me not understand is the Pyrex brand is so strong that the company that it's been licensed to is charging more for the soda lime glass than what you can buy a non-brand name borosilicate container for. So I'm not saying what you should do with this information, right? And there's a chance that the Pyrex brand may someday go back to selling borosilicate glass products. But as of the last time I checked, which was probably last year or so, so I'm a little out of date, but so far as I've heard, they haven't changed any. The last time I heard, Pyrex home use glass was not safe for stovetop use or use in the oven. So if that's something you want, you're going to have to go with a different brand. And some of the less well-known brands were, at least, like I said, Last time I checked on this was a while ago. But at the time, they were selling stovetop safe products for less than the non-stovetop safe brand name products. I think that's just how how things go sometimes. Yeah, same thing for your ceramics. I know some people that put their coffee mug directly on the stovetop to heat up their coffee or their tea. Before you do that, you should really check what kind of ceramics you have, because some ceramics are stovetop safe, some of them are not. And if you're the sort of person that likes to do that, you should make sure you're buying the ones that are safe. The cute mug at the souvenir shop is probably not safe. Just as a heads up, right? It costs more to make a stovetop safe vessel than it does to make one that is safe only to put on the counter. So, in any market where profitability is the main concern, you are not going to get the high performing stuff. That's how the world works. And tourist sales are one of those places where profit margin is the only thing that matters, because selling things to tourists, those tourists take those things and they take them home, and as often as not they put them on a shelf, right? They're not for use, they're for helping trigger the memory of the vacation, right? So even if they're a little bit expensive and a little less functional, we're generally okay with that, because we're not looking for function. We're looking for a reminder of a time that we had fun. Because that's how our brains work. We see something that we associate with fun times, and it helps us to remember the fun times, and it makes us feel better. Right? So there is value in these high-cost, low-performance souvenirs. Right? It's just generally not the value of whatever it is that they're pretending to be. Because what they actually are is a memory trigger. They're not a mug, not a keychain, they're not a this or a that or a postcard. How many people actually send the postcards that they buy on vacation instead of taking them home and putting them in a binder with their photographs? Right, it's kind of like it's the same thing, the same idea as taking photographs, right? We don't take photographs of events because the photograph has some sort of intrinsic value. We take the photographs because it helps us remember. Oh, that's a perception topic, is how reliable are memories? The answer is not very. Most of the things you remember did not happen the way you remembered them. Like, the actual events may have been relatively close to how you remember it, but if somebody comes back and asks you the details, you might think you remember the details, but chances are it's just your brain making up details that seem like they make sense in context. Right, our brains mostly collect big ticket information. We remember details about things that are moderately traumatic. Right? Things that caused us a medium level of pain. Because our brain thinks those are important in order to avoid the suffering that we had that time. We should remember what caused it. But the catch is that if you push that too far, if you're traumatized too badly, that completely overrides your memory response. Like your memory response shuts down entirely, and then you have like no details of anything. You can barely remember what happened at all. And the problem with that is that when you have a memory that's full of holes like that, your brain will just fill them in. So when something is too traumatic, the the thing you remember is not very accurate at all. The most accurate part that your brain remembers is how much you've suffered, right? It doesn't remember the details of the incident at all, which is a big problem when it comes to going to court, right? Because there are a lot of people who, like, if they're a victim of a crime, it's fairly common that the trauma level has pushed them over that memory overload limit. Right, so we've had a lot of issues where a witness was sure the suspect did it. Like, absolutely sure. Not like getting on the stand and lying or making things up, but like they had actual memories in their brain of the suspect doing it, only to find out later that it was somebody else. Right, and that's the danger is when a memory has a hole in it, our brains will fill that hole. Somebody asks us for a detail that we don't have a memory of, instead of realizing that we don't have a memory of it, our brain will make up a memory. Like, that's just a thing our brains do. Our brains are very good at justifying why a certain piece of information fits into a hole without running that past part of our brain that's in charge of our consciousness. Right? The front part of our brain is the part that we think of as ourselves. Right? The back 2/3 of our brain is not the piece that we think of as our personality. Right? It's all mostly automated stuff. It's not 100% automated, but most of the back 2/3 of our brain is right. It's automation. And it doesn't always consult the front part of your brain before it does something, which is problematic sometimes. We've got some really slightly freaky experimental results from people who have had damage between the two sides of their brain. Right, the left and right sides of our brain have a bunch of nerves that connect between them, and there are people who have either had damage from, either a congenital condition or an injury, or who have had those connections severed surgically. Because sometimes those sections are involved in traumatic and life-threatening migraines or seizures. More seizures, I think. I think migraines is either not common or something my brain just made up because I couldn't think of the word that I wanted. I think we try to avoid that now. Seizure medication has gotten a lot better. So surgery always was kind of a final option, but we have more options to try first now. But some of the research on these people it's very disconcerting. Because some of our perceptions are only processed by the left half or the right half. So when most of the connections between the two have been severed, like sometimes one half will get some of the results from the other half, right, but is not getting the actual raw data. So one of the experiments that researchers have done is showing pictures of things to people who have this condition, have this split-mindedness. And then, like, one side is responsible for speech. Like, speech is only on, I think it's on the left side. So they'll show a picture. They'll set a picture off to the side so that only the right side of the brain can see it, because I think the right side of the brain is responsible for the left half of our field of vision, and the left side is responsible for the right half of the field of vision. I don't know why it got crossed like that, but it's in both eyes. So the left side of our vision from both eyes goes to the right side of the brain. Right, but speech is in the left side of the brain. So if you put the image off to the left, so only the right side of the brain can see it, right? We don't totally understand it, but there's apparently still some connection between the two sides, because the right side of the brain will pass some of that information over to the left side. So if you ask the person what the picture is, they'll say they can't see it, because the part responsible for speech cannot see the picture. But then if you ask them to guess what it is, they'll guess correctly. Right? So the speech part of the brain doesn't realize that the other half of the brain can see the object. But if you ask them to guess, that information has been passed and they'll get it right, which is very disconcerting. I think somebody, one of the educational YouTube channels did a video on that. Sorry, I don't remember who it is. It's one of the big channels though, so if you search for it, it'll pop up right towards the top of the list, and I recommend it because they explained it a lot better than I did, with lots of animations and nice background music and stuff. But yeah, it's very disconcerting how much of our brain runs on automatic. Normally, you think the piece of your brain that talks is under the control of the piece of your brain that plans, right? Our forebrains, where our personality is and where many of our memories get stored, right? That's the part that's responsible for long-term planning and even relatively short-term planning as well, right? Like that's the piece that we consider us. The part that talks is more automatic than we would like to admit. If you've ever said, "Oh, I spoke before I thought about it," you were much more literally correct than you probably meant. It's a very disconcerting note. Yeah. Perception is weird in general. It's a very disconcerting topic. Oh, another way of doing this demonstration is to so you can some shapes, squares. shapes, squares. Make that right. So back. And if you look at the right side, it looks orange. And if you look at the left side, it looks brown. And if you look at the middle, the brain is probably trying to put a line in the middle of the bar, even though it doesn't exist. If you look at like, just this piece right here down at the bottom, it might actually look like it's curved a little bit. Because on the left side, brain is trying to convince you it's brown, and on the right side, it's trying to convince you it's orange. Right? But on the top, it sees that's a smooth, continuous color. So this place here where all three colors border, it might try and convince you that it's actually rounded there. It's not. It's just a rectangle. All three of those lines are flat. All three of those colors are continuous colors. Some people find that very upsetting. I wonder how this one does with gradients. So there's some similar experiments that are based on gradients. So I want linear gradient. Sure, 180 is fine. I guess if I want to line it up with it, it's 2.0, it's fine. I want the leftmost side to be as white as my computer can go, and I want the rightmost side to be as black as my computer. When you look at that, it looks like the orange line also has a gradient, but it doesn't. It's the same color all the way across. Alright, I've been yapping for 3 hours. And my throat's getting a little bit sore. I haven't eaten anything in a while. So I think I'm going to sign off. Didn't make any progress on my existing topics, but just added more topics to the list. It's weird. I keep doing that. Well, if I can find a good designer and artist, then maybe I can start getting some of these storyboards turned into actual videos, and then I'll consider that good progress. That's really where I need to get some motion in the next couple of weeks. Yeah. In the meantime, this weekend, I think I'll go back over some of my yapping and slice out some excerpts of things that I've talked about. That way, at least if anybody comes a knocking, they'll have something to watch without needing to filter through the live streams to figure out which things are most entertaining or the most interesting. But not tonight. For tonight, it's time for dinner, and relax a little bit, then go to bed early, and get up early tomorrow, and work hard. So, see you next time. Thanks for stopping by.